What is one aspect that makes long-term space missions that involve setting up bases impossible in status quo? Transportation. Transportation is still singly one of the biggest challenges we face when it comes to setting up bases. Carrying everything we need from Earth is neither practical nor sustainable. However, all of it wouldn't be a problem if only we could harness the resources available at our destination. The future of space exploration and long-term manned missions lie here. As easy as the solution may sound, it is not so. Our destination may have all of the universe's untapped potential, but all of it exists in a state that can't be used directly by humans. Enter microorganisms. They've been doing this very job since the advent of all life on the erstwhile hostile Earth. They are evolutionary conditioned to not only survive, but thrive and reach peak performance and produce life sustaining products in their own habitats. Now, with the help of genetic engineering and synthetic biology catching up pace, we can finally utilize raw materials such as Martian regolith in Mars into human useful products without having the need of transporting them all the way from Earth. Take silicon, for instance. It's one of the most abundant elements on Mars, yet it remains an untapped resource. Unlocking its potential could revolutionize how we approach resource utilization in space. Our project, Co-Culture with Silicon Mobilization for Biomanufacturing using Martian regolith, or in short, Cosmobiome, presents a solution to harness the potential of Martian regolith for sustainable biomanufacturing. It focuses on developing a novel co-culture system. It establishes a symbiotic relationship between two microorganisms working together to mobilize silicon from Martian soil and utilizing it to produce a useful product. Our idea involves four parts. One, harnessing Martian minerals. Anorthosite, a mineral abundantly found in Mars with a chemical composition similar to calcium aluminosilicate, will be used as a silicon source. Two, symbiotic relationships. P. fluorescens, a bacteria, and P. tricornitum, a diatom, share a symbiotic relationship that supports each other's growth. Three, nutrient recycling. We use Pseudomonas fluorescens for silicon solubilization and Phaeodactylum tricornitum for silicon utilization. This co-culture setup establishes recycling of nutrients. 4. Versatility. Both organisms can be genetically engineered to produce different products of interest.
Pseudomonas naturally produces GDP or geranyl diphosphate. So we decided to engineer a limonene synthesizing pathway for the production of the enzyme limonene synthase so that GDP could be converted to 4S limonene. Limonene is used for pharmaceutical products given its anti-cancer properties and as a flavoring agent. The genetic circuit was assembled using B sal as exonucleus, following the Golden Gate assembly. The bacteria is to be transformed upon electroporation. Moving forward, we plan to create a co-culture to measure growth dynamics. Afterwards, we'll use Gibson assembly to engineer plasmid vector backbone and transform diatoms using electroporation. A new co-culture will be set up with transformed diatoms and bacteria to measure growth dynamics again. Finally, we'll qualify and quantify acetaminophen production in the recombinant diatoms and co-culture setup. Coming to results, we successfully showed silicon solubilization by the bacteria. Here, as seen by the color change from blue to yellow in the presence of Pseudomonas fluorescens. When we cultured the bacteria in a Martian soil simulant, we observed an intriguing phenomenon, which was an oscillatory behavior in their activity. This behavior aligns with the findings reported in the well-established literature. Our observations revealed an interesting trend in the growth rates of the diatoms. When silica was present in the environment, we noticed significantly higher growth rates as compared to in conditions where silica was absent. These findings underscore the importance of leveraging local resources like silica on Mars to optimize biological systems for extraterrestrial applications. We successfully assembled the plasmid via Golden Gate with limonene synthase and transformed into the bacteria. Finally, in co-culture, we were able to show dysynchronized growth rates of both the diatom and the bacteria. This suggests symbiotic relationship between the two.
To complement our wet lab work, we modeled a couple of aspects of our project. We used constraint-based modeling to optimize production of limonene by the bacteria and modeled the co-culture using the MyCom framework for community modeling. We used several algorithms to simulate the fluxes across growth and product synthesis pathways. To visualize fluxes across a network, we expanded the Escher tool to our diatom from its current limitation to E. coli and yeast. To optimize production of our desired compounds, we identified targets for gene overexpression using the FSCOF algorithm. Through our community modeling, we show that the growth rates for bacteria and diatoms are cooperative in nature, which leads to our in silico validation of the initial hypothesis of the symbiotic relationship. With the presence of solubilized silica in the community, the diatoms increased growth, matching our wet lab results. Zeroing into a chassis for genetic engineering is something researchers face on a day-to-day basis. To help solve this issue, our team came up with a software project which has been developed into a web tool, Astrolabe. Our software pipeline facilitates analyzing and identifying SymBio hosts based on available resources and growth conditions as user inputs. The aim is to gather relevant resources from the user, perform pre-processing, search for metabolic data, find resource utilization pathways, and ultimately provide a ranked list of potential chassis that comprise these pathways. In the web tool, the user enters the common name of a molecule. We have chosen the Chebby standard for input, as it provides a cataloging of a wide array of chemical formats and offers easy code integration via its API. Also, the user can input query-related information, such as required physiological conditions, for example, temperature or pH. Upon receiving these input parameters, the software executes a search for specific reactions of these resource compounds and metabolic pathways comprising these in several databases, such as BioSec, UniProt, KEGG, and Brenda. These metabolic pathways are then matched to potential hosts. Finally, to rank a specific chassis, we have a scoring function which scores the available chassis based on two key criteria: resourcefulness and survivability. We also developed a command line interface version of our web tool that can be integrated into larger software pipelines as per user requirements. In a country of over 1 billion young minds, competitive exams often reduce biology education to rote learning for the rankings, overshadowing the true beauty of the subject. Having experienced this ourselves, we deeply understand the systemic flaws in education and aim to address them by providing an engaging, well-curated learning experience. It has been shown that gamified collaborative learning enhances student engagement. Guided by this philosophy, we focused on active engagement through hands-on workshops, interactive sessions, and educational games tailored to students' knowledge levels. Our efforts centered on the values of inclusive access, innovative thinking, collaboration, open dialogue, awareness, and curiosity. The face of our gamification efforts this year was the SynBio Monopoly game. Similar to how a traditional Monopoly board groups streets by neighborhoods, our game treats each color as composite systems, each containing multiple parts. Players start as chassis, collecting genes and parts as they progress. Utility cards feature tools like gene guns and incubators. To make synthetic biology accessible to younger audiences, we also created a synthetic biology activity book featuring interactive tools like comics, mazes, coloring pages, and matching games to introduce fundamental concepts of DNA, genes, and genetic engineering in a fun and engaging way. In attempts to educate young minds about symbio and simulate curiosity, we conducted a Symbio Symposium, a seminar on space synthetic biology, and a high school webinar about introduction to synthetic biology. We visited a few schools and engaged them with Symbio Monopoly, activity books, a dice-based base pair game, and quizzes. We also were part of various other initiatives where we got in touch with people from academia as a way to incorporate their expertise in our project. As our project was related to in situ resource utilization in space, we got in touch with space organizations like NASA and ISRO to understand the feasibility of our project. We got in touch with policy experts in the field and also conducted events to help build awareness to the general public. This is the team involved with the project. A special thank you to our sponsors.